Today we're going to be graphing polynomials, and let's first look at some basic graphs of polynomial functions so you can see some general characteristics and attributes of different polynomial functions. A polynomial function is a function whose rule is a polynomial, which we've discussed in previous videos. In this lesson, we will only work with polynomials in one variable. Graphs of polynomials are continuous. What does this mean? This means they continue. They have no gaps, holes, or breaks. They're smooth with rounded turns. They have no points, no cusps. Polynomial end behavior. Let's talk about on the ends. Or you know what? Before I talk about the ends, let's go through several of these polynomial functions. You first might see something like this, a constant function, where you have something like y equals 4, okay? Where there's no x variable, there's just a constant. And what you get is a horizontal line. That's a constant function. Then you might recall, or you're probably very well versed with linear functions. Linear functions produce lines. Their degree is 1. So something like y equals 2x minus 3, right? That's a linear function. And then you've also worked with quadratic functions. Quadratic functions look like this on your graph. They form parabolas. The degree is 2. Let's move on to cubic functions. Cubic functions are something like, y equals x cubed. That's the parent cubic function, and that looks something like this when graphed. That's your parent cubic function. But what you have right here is just a general kind of the shape of a cubic function, what it might look like when graphed on a coordinate plane. And so as you can see with this function, if I go back to this quadratic function up here, the ends of it end in the same direction, right? So your parabola, they're both ending up, or they're both gonna end down, right? Your parabola is gonna open up or it's gonna open down. If you look at a cubic function, on the ends out here, right? These are the ends. On the ends out here, they don't end in the same direction, okay? If one is going up, the other is going down. That degree is a 3, or it's a third degree function. A quartic function like this, again, it kind of resembles the quadratic function in that it ends in the same direction, right? Both are up or both are facing down, but you've got these like different amount of turning points on the inside. Then you have a quintic function, fifth degree function, and again, it's similar to a cubic function because on the ends, it ends in different directions. Like one end goes down, the other end goes up, okay? So let's look at end behavior, like I just discussed. End behavior of a polynomial function describes what the polynomial is doing on the horizontal ends. Okay, that's why I drew these arrows right here on the ends. So those odd degree functions, for example, and let me erase some of this just because there's kind of a lot going on. Those odd degree functions, I'm going to put this in a different color. Odd degree functions are like this linear, this cubic, this quintic. Those are odd degree functions, and they end in opposite directions. As x approaches infinity, f of x, which is just fancy for y, approaches infinity. So like, for example, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity, right? Negative infinity, y is also approaching negative infinity. But those even degree functions, like those, the parabola, right, the quadratic, the quartic, those even degree functions, they actually end in the same direction. So as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches infinity again. So that's end behavior of polynomial functions. And it really, those even degree functions end in the same direction. Odd degree functions do not. Let's move on to attributes of polynomial functions. So there's a lot going on. Here's just a cubic, just some graph of a cubic function. And we're going to label some different attributes of this function. Let's first look at the end behavior here. The end behavior for this particular graph, as x approaches infinity, f of x approaches infinity as well, right? And as x approaches negative infinity, f of x approaches negative infinity. So we want to make sure that when we look at a graph, we can describe its end behavior based on what we see. What is it doing on the ends out here, right? On the ends. Let's now look at these relative extrema. Okay, so these relative extrema are right here. Okay, those are those turning points. And that's actually another thing that they're called. This is called a relative maximum. It's called a turning point. You might see it as such. It's a turning point. It's also called a local maximum. Sometimes you'll see local maxima, relative extrema. They all mean the same thing. This relative maximum, it's not the absolute maximum of this graph, because as you can see, the function will continue to go up on this right side over here. So it's not an absolute maximum, but it is in this particular area right here, and what we're looking at over here. So we call that a relative maxima. A relative maximum. All right, let's look at this relative minimum down here, also called a local minimum, also called a turning point, right? It's a turning point. It's where the function is turning, and it's going to switch directions. It's going to move from decreasing to increasing right there. So that's what those are called. Those are just some new vocabulary words for you. And then we have zeros right here, which you should be familiar with at this point. Your zeros are just where your function crosses the x-axis. So those are your x-intercepts. Also called roots. What are the roots? Also called solutions, if you want to put that on there. Solutions. Okay, and they're the x-intercepts, which means those are the values where y is 0. The x values when y is 0. Okay, so where it crosses the x-axis. So this particular function, it's a quadratic, degree of 3, and how many solutions does it have? It has 3 solutions, 3 roots. How many turning points does it have? It has 2. What are those turning points, or what is that relative maximum? Negative 3, 4. What's that relative minimum? 0.5, negative 3. Okay, let's move on to intervals where the function is increasing. So where is it increasing? It's increasing when it goes up from left to right. Okay, so it's increasing right here in this interval and this interval right here. And how do we write that interval? We write it from left to right. So it's from negative infinity to negative 3, right? Because we include those domain values. And 0.5 to infinity. Okay, so there we go. And that's how we would write the intervals where the function is increasing. And there's 2 intervals there. Let's look at where the function is decreasing. It's decreasing in this interval right here, which is from negative 3 to 0.5. And I know that looks like an ordered pair, but it's not. But at the point where the, at that relative maximum and that relative minimum down there, we can't say that it's doing anything at that specific point. It's neither increasing nor decreasing. So we want to make sure that we use these parentheses and we do not have brackets. Okay, so let's move on to end behavior. We're going to talk about end behavior again. This end behavior in this, we really want to point out the difference between those even degree functions and those odd degree functions. How is it going to behave on the end? This says to graph the following even degree functions. What do you notice about their end behaviors? So f of x equals x squared. That looks like this, right? It's your parent quadratic function. And what's happening? It's ending in the same direction. What about negative x squared? Well, we know that negative out front is going to reflect it across the x-axis. It's opposite y. So instead of opening up that negative a value out front, it's kind of messing up for me right here. That negative a value out front is going to flip it and it's going to open down. So what do you notice about their end behaviors? They end in the same direction. That's something that I notice. And what else do we notice? A positive a value ends up Let's say that. A positive a value ends up, opens up, ends up, and a negative a value, right, which is that value in front, right? It's that leading coefficient, if you will. That negative a value ends down. So I think that's a good observation. And let's move on to those odd degree functions. Graph the following odd degree functions. What do you notice about their end behaviors? F of x equals x cubed looks like this. It's your parent cubic function, and it takes this shape right here, where it starts in the lower left, it increases like a linear function would, but it does bend and curve, right? So it kind of bends at the x-axis. If you have this negative out in front right here, f of x equals negative x cubed, it's going to look like this. And it's going to start opposite, right? And so we know that this negative out front is opposite y. So it's like this flips down here and this flips up there. That's basically what happens. Okay, so it looks like that. So let's make some observations. What do you notice about their end behaviors? Well, they end in opposite directions. They don't end in the same direction as with the two up top. So they end in opposite directions. Let's write that down. They end in opposite directions. And a positive a value, that first one that we graphed, what happens with it? A positive a value goes from lower left to upper right. And then what do we notice about the negative a value? The negative a value goes from upper left to lower right, right? So knowing what you know about this graph, the end behaviors are different, right? They're opposite. This one right here, as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches negative infinity. This one's different. As x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches infinity. So we just need to make sure that we really get those, how we describe the end behaviors. You know, we're precise in describing that. So now let's move on to the number of x-intercepts and direction changes that you'll see with different polynomials. What I want you to do is use your calculator to graph the following functions. Complete the table by stating the degree, the number of x-intercepts, and number of direction changes for each polynomial. So pause the video and do that now. Just plug these into your calculator. You can go to Desmos, or you can plug it into your calculator and just write the degree right here, right? That's that highest coefficient, or not coefficient, highest exponent. The number of x-intercepts, how many times does it cross the x-axis? Number of direction changes, right? Those are those turning points or relative extrema. So go ahead and pause the video and do that now. Now let's answer some of these questions. What do you observe about the degree of the function and the number of x-intercepts? Do you notice anything? I notice that the number of x-intercepts is never more than the degree of the function. The number of x-intercepts is never more than the degree of the function. What do you observe about the degree of the function and the number of direction changes? Well, the number of direction changes I'm noticing is never more than one less the degree of the function. The number of direction changes is never more than one less the degree of the function. And that's actually true for polynomials, both of these. So the number of x-intercepts will never be more than the degree. You can have the degree is the maximum amount of x-intercepts that a particular polynomial function will have. And the number of direction changes is always going to be one less, and then at least, right? Or at most, I'm sorry, at most it will be one less, and then you subtract 2 every time after that, right? So you can have 4 direction changes for a polynomial degree of 5, and then maybe 3, and then 1, but you're not going to have something like 3 direction changes. Did I say that right? 4 and then maybe 2. I'm sorry, I didn't say that right. So you might have 4 and then maybe 2, but you're never going to have like 3 or 1. Okay, let's move on to real roots of a polynomial. These are long notes. Sorry, there's a lot to get through, a lot to look at. Real roots of a polynomial are the x-intercepts. We can find the roots of a polynomial by factoring and using the zero product property to solve for the solutions, as we've done with quadratic functions. What do? You set each factor equal to 0 and solve for x. That's how you use that zero product property. In the example below, the function f of x is written in both standard and factored forms, which factored form is just intercept form. We can see the x-intercepts. Draw a sketch of the function on the graph provided. So I've got the function written in standard form right here. After it's been factored, it looks like this, which actually on this particular one, you cannot factor it, but I know the x-intercepts and it looks like this. So what do you have here? You have a third degree function. So I know that end behavior, right? It's gonna end down here and up here. I know what the end behavior is like. And now we have 3 x-intercepts. And what do? I set each of these equal to 0, and I solve for those x-intercepts. And this is how we use the zero product property, right? So x equals -6. So now I've got my 3 x-intercepts. I've got one at -6, one at -2, and one at 3. And I know the end behavior. So if I'm just drawing like a rough sketch of what it's going to look like, I know it's going to start down here, cross through that x-intercept, go down, cross through that x-intercept, and look something like that. Now, is this exact? No, I don't know exactly what this looks like, but I know a general shape and pattern of what this function is going to look like. And I can graph it knowing the end behavior and the x-intercepts. Looking here, polynomial functions don't always have roots that cross the x-axis. So it doesn't always do this right here, what you see at every single root, where it just crosses. Okay, that makes it really nice and simple. We can determine the end behavior of the function, or the behavior of the function at these roots, from the multiplicity of the zeros. So here's something new. The multiplicity of a root is the number of times x minus r is a factor of the function. Okay, so what does that mean? Let me show you what that means. Odd multiplicity occurs, and I'm actually going to do this again. Odd multiplicity occurs when the factor has an exponent that is odd. Even multiplicity occurs when the factor has an exponent that is even. So rather than just read through all that, I'm going to show you what this looks like. That tends to help students a little better. So let's say when you've factored a function, or you've got it in factored form, and it looks like this, okay, where f of x equals x minus 3. I would say odd multiplicity of 1 because the exponent on the outside of the function, or of the factor of those parentheses, is just 1, right? We don't see an exponent, so it's assumed to be 1. Well, I know that x-intercept is going to be at +3. And this is a line, right? I can see that, right? X minus 3, it's linear, so it's just going to cross this x-axis right here, right? So it'll just cross that x-axis. That's how it's behaving at the root, or at the x-axis, right? X-axis, y-axis. Let's look at even multiplicity. I'm going to show you what I mean by that. Even multiplicity, as you can see, we have an exponent that's even, right? 2, 4, 6, 8, you can continue. What happens at the root when you have a multiplicity that's even? Well, I know that x-intercept is still going to be 3, but how is this function going to behave? When you've got even multiplicity, at the root, it's just gonna bounce off and end in the same direction, okay? So it just bounces off. It doesn't cross that x-axis, it actually bounces off. Let's move on to the last one, which is an odd multiplicity greater than 1. So we know that if it's got an odd multiplicity of 1, it's just going to cross that x-axis and it's a line, okay? Well, if you've got any other odd multiplicity greater than 1, right? So 3, 5, 7, 9. What happens? Well, I still have a root at positive 3. But in this case, it's actually going to kind of bend or wiggle at the root. So it just bends. It doesn't just cross it, it kind of curves. Okay, so let's move on and let's try to graph some of these polynomial functions using these particular rules. In this first one right here, and I'm going to change colors here. In this first one, I have f of x equals x minus 4 squared times x plus 1. So what are the roots of the function? I know the roots of the function are going to be positive 4 and negative 1. Positive 4 and negative 1. And then I know I have an even multiplicity at the root of positive 4, right? So I know at positive 4, I've got even multiplicity. You know what? I've graphed that wrong on my answer key. So I know right here, okay, at this particular root right here, it's got even multiplicity. Here, it's got odd multiplicity of 1. So what happens? I know that it's going to cross that root right there, and it's going to go up, and it's going to curve, and it's not going to cross that root. It's got even multiplicity. It's going to go up just like that, okay? So that's what the function is going to look like when graphed on a coordinate plane. Right here, it's going to bounce off. And then right here, it's going to cross. Okay, and that's just because of the multiplicity at those roots lets me know the behavior of what the function is doing at those roots. Is it going to cross? Is it going to bounce off? Or is it going to bend or wiggle? So let's move on to the next one. F of x equals x plus 2 cubed. Ooh, lots going on here. X minus 6 times x minus 6 squared times x plus 4. We'll just say raised to the power of 1. So looking at this, I can tell that the degree of the function is you're going to add the multiplicities. So let's write that down. The degree of the function, you're going to add the multiplicities. So I know the degree of this particular function is 3 plus 2, which is 5, plus 1, which is 6. So the degree of the function is 6. So I know that on the ends, it's going to end in the same direction facing up. And I know it's facing up because I don't have a negative out front right here. If I had a negative out front, it would be ending down. So what's happening here? Let's see, we've got a root at negative 2. We've got a root at positive 6. And we've got a root at negative 4. Okay, so I know we're starting up here, right? We're starting up top. And I know we're going to cross this particular, oh gosh, this is going to be kind of an ugly graph because I'm going to walk through it. We're going to cross this graph. We've got our next intercept that we're looking at is this x equals negative 2. And because it has a multiplicity of 3, I know it's going to bend at that root. So it's going to come down here and go up and kind of bend at that root. See, it's kind of an ugly graph. And then we're going to move on to, did I do that right? Oh, yep, this next one over here, where x equals 6. Okay, that's the root over here. The graph is going to come up and then go down and bounce off that root. And I know it's going to bounce off that root because it's got a multiplicity of 2. So what's happening at each one? It's going to cross this one. It's going to bend at this root. And it's going to bounce off at this one. Okay, so that's what's happening at each of those roots. So let's go through and do kind of a little recap of graphing polynomials. When we're graphing polynomials, the first thing I want to talk about is end behavior. Determine the end behavior by the values of a and n. A being the leading coefficient, so is it positive or negative, and n being the degree of the polynomials. Polynomials of an even degree approach the same on both ends. So when a is greater than 0, even degree function might look something like this. When a is less than 0, so there's a negative out in front, it would end like that. Okay. Polynomials of an odd degree. Now, I'm saying you could have something like this, right? That could be a function right there, okay? But it'll end in the same direction. That's end behavior. Polynomials of an odd degree approach the opposite on both ends. So you might have something like this. Okay, that's a cubic function where a is positive. And then when a is negative or less than 0, it approaches the opposite direction, right? So it flips, right? It's a reflection across the x-axis, and that changes the end behavior. Let's move on to turning points. Turning points. Turning points. Turning points are where the graph changes from increasing to decreasing and decreasing to increasing. These are also referred to as local extrema, relative extrema. To find the maximum number of turning points a graph will have, subtract 1 from the degree. That's the maximum number. They can have less. Okay. Let's move on to real roots. Real roots. Real roots. Roots are the zeros or x-intercepts of a polynomial. To find the maximum number of roots a graph will have, start with the degree. And then multiplicity of those roots. What is the function doing at those roots? How is it behaving? We can look at multiplicity to determine this. Odd multiplicity, right? That exponent right outside the parentheses when it's in factored form. If it's odd, the graph will cross the x-axis. An odd exponent greater than 1, it'll bend, right? So it'll cross, it'll bend. Even multiplicity, if the exponent is even, the graph is going to bounce off the x-axis. So to determine the degree of the polynomial in factored form, we add the multiplicities. And that lets us know end behavior, which helps us a lot when we are sketching the graph of a polynomial function. So I know these notes were long, but hopefully they gave you a lot of information to help you graph polynomials well and really understand end behavior, roots, and kind of what's going on with the graph of a polynomial. I hope it was helpful.